Here's the solution to homework set number 7 for ECE 320. The first problem looks at a DC to AC converter. Given the circuit, find the voltage at V2. So what's kind of happening in this circuit, I've got a Boolean output, a square wave, turning on and off Q2, and nodding it, turning on and off Q1. So these kind of alternate. When Q2 turns on, current flows up. When Q1 turns on, current flows down. So if we look at the current from the transformer, it goes up, down, and there's your zero line. That's coupled through a transformer, so the voltage V2 also goes up and down. This is trying to create an AC signal at V2. What the capacitor does is it kind of forms an LC resonant circuit or a filter. It tries to filter out the harmonics, just leaving the first harmonic, 60 Hertz. If I run this in Circuit Lab, do a time domain simulation for a couple cycles, here's what I get. It's not 60 Hertz. It's actually about 180 Hertz. The RC resonant circuit is about the third harmonic. To fix that, what I can do is change C. Theoretically, for an LC tank, the resonant frequency is 1 over LC. That's omega naught squared. I want that to be 60 Hertz, so C should be 70 microfarads. That didn't quite work, so just kind of play around with C and rerun the simulation. I found out about 100 microfarads. It works fairly well. That looks almost like a sine wave. What that means in terms of efficiency, most of the energy is in the first harmonic, so you're close to 95–98% efficient on a DC to AC converter. I'm converting on the circuit, 24 volts DC into AC, and most of the energy is in the first harmonic. It's almost a sine wave. Problem 3 looks at come up with the differential equations for a circuit. And it's actually not that bad. Sounds intimidating, but not really. What you got to remember is for an inductor, the voltage across an inductor is L di dt, and I'll use the dot to be in derivative. For a capacitor, the current through a capacitor is C dV dt. So for this first inductor, the voltage across it, V1, is L di dt, 0.1 I1 dot. That's the voltage on the left, which is 10 minus this voltage. That's I times R. The current is I1 plus I2 for conservation of current. That's the voltage on the left. Voltage on the right is V5 plus 30 times I1. So minus V5 minus 30 I1. For V2 dot, this guy right here, voltage on the left, again, is Vn minus 1 times I1 plus I2. The voltage on the right is V4. Gives me the second equation. Third equation, V equals L di dt. V3 is 0.2 I3 dot. That's V5 minus V6. For capacitors, the current I equals C dV dt. I4 is 0.01 V4 dot. That current is current in minus current out. Current in is I2. Current out is V4 minus V5 over 20. I5 is C dV dt, 0.2 times V5 dot. That's going to be the current from the left. V4 minus V5 over 20, plus this current, that's I1, minus I3. And then this current is just I3. So these are the 6 coupled differential equations that describe that circuit. Problem 4 is analysis of a semiconductor relay. Assume a 45-degree firing angle. Find the voltages at V1 and V2. Now note this has 4 diodes. What that means is if I have a sine wave, let's do this in yellow. Here's your sine wave. And the minus sine wave, sort of. I've got a 45-degree firing angle, so it doesn't turn on until 45 degrees when I follow it. The second diode doesn't turn on again for 45 degrees. So this is what the waveform looks like. I go 45 degrees past 180. The DC voltage is the average. The AC voltage, roughly, is the peak to peak. So the DC voltage is this one. Here's the correct equation. Twice times 20 volts cosine of 45 degrees over pi shifted by 45 degrees, or shifted by minus 1.4 volts, because at any given time I've got two diodes turned on. Gives you the DC voltage of 7.6 volts. The DC voltage to V2, then by voltage division, is 100 over 100 plus 10 times the DC voltage to V1, 6.91 volts. The AC voltage, that'll be the peak right here to the minimum. That'll be your 20 volts times 1 plus sine of 45 degrees, 34.14 volts. That's the peak-to-peak voltage. The voltage at V2 then is at 120 hertz. Find the impedance of the inductor. Find the impedance of a capacitor, minus J33 ohms. Put these in parallel, 9 minus J29 ohms. Then it's R1 over R1 plus R2, a voltage divider, times V1. So it's going to be your R1 over R1 plus R2 times the input voltage, gives you the voltage of V2, 5.4 volts peak to peak. We'll check that a little bit later. Well, actually, let's check that now. The differential equations for that circuit are this one. C dV dt is the current through the inductor minus the voltage across the capacitor over R. The voltage across the inductor, L di dt, is the input voltage minus 10 times the inductor current minus Vc. So once I have those differential equations, we'll talk about that on the upcoming problem. I can then simulate it. I know the voltages and the current. I can find out how they're changing. Integrate. Repeat for the entire cycle. And just to get out of the transient, let's do that for 40 cycles. And here's what it looks like. Here's my first cycle, second, third, fourth, going for 40 cycles. Kind of looks like a steady state. The blue line is V1. The red line is V2. That's solving it numerically. Once I have V2, I can find the AC and DC voltage. The DC voltage is the average. The AC voltage is the peak to peak. So the average is 6.92 volts, and the peak to peak is 4.24 volts. So 6.92, 4.24, 6.92, about what I calculated, 4.24, a little off. Again, the reason I'm off on the AC voltage is I'm assuming the first harmonic in the Fourier transform is the peak-to-peak voltage. It kind of looks like this. I'm taking that as the first harmonic. That's close, but a little bit wrong. To be more accurate, I should be using Fourier transforms. But for this class, good enough. Problem 5 is a design. Design so that V2 is 9 volts DC, 1 volt peak to peak. To do that, I plug it in the equations. I know the voltage of V2 is 9 volts, meaning the voltage of V1 has to be 9.9 volts. Again, you've got this circuit, inductor, capacitor, that's resistor. So if this is 9 volts, by voltage division, V1 has to be bigger. That's 9.9 volts. To get 9.9 volts, I can calculate the firing angle. Should be 27.4 degrees. To find C, let's assume the capacitor is not there. Then by voltage division, I have my load, 100 ohms, over 100 ohms plus the inductor, times the input, 11.6 volts peak to peak. To make it 1 volt peak to peak, I want to make the capacitor reduce the 100 ohm resistor by a factor of 1 to 11. I want it to be 8.6 ohms. Solving, omega 754 radians per second, solving for C. C should be 154 microfarads. To check that, take this circuit, write the differential equations. The inductor, V is L di dt. This voltage is V1 minus IL times 10 minus V2. This current is IL minus this current, minus V2 over 100. So when I go out and simulate that, so I change the firing angle to 27.49 degrees. the capacitor to 154 microfarads and let her run. It goes 40 iterations, and hopefully I'm at steady state. There's my answer. I can then check. The average voltage is 9 volts. I calculate for 9, so that matches up. The peak-to-peak is 0.85 volts peak-to-peak. I designed for 1 volt peak-to-peak, a little bit off because I'm using approximations. Assuming the first harmonic in the Fourier transform is this distance, that's your 120 hertz, your V1 peak-to-peak. A little bit wrong, so my answer is a little bit off. If I want to be more accurate, I should be using Fourier transforms. So that's homework set number 7 for ECE 320.